All right, so welcome to today's lecture. So today we're still looking at thermodynamics, and under thermodynamics, we're looking at the laws of thermodynamics, and we're going to start with the work in thermodynamic processes. All right, so let's look at, let's quickly go through the slide. Yeah, so today's slide is quite short. We're not going to take a lot of time, but of course you have to do a lot of calculations in your exercise. Yeah, so at the end of the the topic, I think I'll prepare something like a tutorial which we'll have to do together online. Yeah, so that at least I can show you some of the tactics which you can be using to solve some questions. Okay, so let's quickly begin. So we're going to start with work in thermodynamic processes, and then from there we look at the first law, and then thermodynamic processes in gases, and then thermal processes in gases, and then today we're just looking at the first law, and then the next time we'll meet to do the second law, then we're done with thermodynamics. So let's look at the work in thermodynamic processes. So I'm sure we know that according to what we already know from grade 12, from high school, we know that work is given by force times distance. So work is given by force times distance. And for instance, if you've been given a piston with a certain gas inside there, and then you try to compress this piston, you know that if the change, if y, if this is y, okay, if the distance from there to there is, if we're calling the distance from there to there as y, this distance, if we call it y, from there to there, if this is y, and then let's say this is y initial, and then this is the final y after compressing. Yeah, so we said work is given by force times distance. So in this case, we can say work is given by force times the change in y. So the change in y will be, so let me just write it here. So the change in y will just be y final minus y initial. So y final minus y initial, we expect this change to be a negative answer, to give us a negative answer. Why? Because our final y is smaller than the initial y. The initial y is bigger, the final y is smaller. So when you subtract a small number from a bigger number, when you subtract a bigger number from a small number, you get a negative answer. So we expect our work after this process to be negative. So we'll have something like this, F change in y. Yeah, so, but again, we know we're dealing with this is thermodynamics. So what we need is to get rid of this F. And we know that F can be written in terms of force. F can be written in terms of pressure and area, as we know that pressure, according to the definition, is the force that works on a certain area, which is a. There's am I the only one experiencing a problem with today's meeting? Can someone confirm if there's a problem, so that maybe we change the platform? Maybe we use Google Meet. But I'm sure most of you are just okay. Okay, so well, yeah, you're also experiencing the same. Okay. All right. So pressure, I'm waiting for the responses. Okay, so pressure, we said pressure Why to just network in your area? It's okay. Here. All right. So I think it's just the network. I'll send the recording at the end of the session. Okay. So pressure is equal to, sorry. So let's make we're trying to get rid of F. So let's make P the subject. I mean, F the subject of the formula. So force will therefore be equal to pressure times area. So our work will simply just be given by, what is F, will put pressure times area and then times the change in Y. But we know that area, we know that, let me just write it properly. But we know that area times any length or any change in the length is just the volume. So if area times length is equal to volume, but if there's a change there, it means that you're having a change in volume there. So this part will just be replaced by the change in volume. So the work in thermodynamics will simply just be given by a negative P change in volume. Negative P times the change in volume. So this is the area, this is the work that we're going to be using in thermodynamics. Yeah, so this is the formula for work that we'll always be using in thermodynamics. Of course, there are also other derived work formulas that we're going to see. All right, so this one is the work done on a gas. It's the work done on a gas. So meaning the work done by the gas will just be the positive of this same function here. The positive of this is the work done by the gas, and then the work done on a gas should have a negative there. The reason why there's this negative is because of the change in Y there. It's always negative if we're doing work on the system, right? But if the system is the one that is doing work, then the work is going to be positive. So these two statements are very important. So let me just put up the notes. So this is what I was trying to derive. So the work done on a gas will simply be given by this formula. And then from there, P, we know that P is the pressure throughout the gas, and the change in volume is just the change in volume of the gas during the process. And then the definition of work in the above equation specifies work done on a gas. Yeah, that's what I'm just from explaining. In many textbooks or in many texts, work is defined as work done by a gas. That's why it's positive. So in many books, you discover that you find a positive P delta V, meaning what they are talking about, if you find work is equal to positive P times the change in volume, means that they are talking about the work that is being done by the system or by the gas, if you are dealing with gases. All right, so in this text, work done by a gas is denoted by W environment, and then in every case, work will be equal to work done. Okay, the positive work, which is just the work done by the gas. I don't know what they meant here, but I think they are trying to explain the same point that I was saying. In most books, you find this work done by the gas to be positive, and then work done on a gas is always negative. Okay, so let's quickly move on. Right, so the two definitions just differ by a minus sign. So let's look at the PV diagrams. So we all know that when you're drawing a PV diagram and then it has a constant pressure, it means that that process is simply just an isobaric process. If you have a constant volume, it's isovolumetric, yeah. And then if you have constant temperature, it's isothermal. It's an isothermal process. Yeah. So that's what it means. So when, for instance, you have an isobaric process like this one, then they ask you to calculate the work of this process, of this entire process. They ask you to calculate the work of this entire process. You simply just find the area under the curve. So the area under the curve is the one that will give you the area under the curve is the one that will give you the work done on the gas. So the work done on the gas can either be positive or negative, depending with the arrow here. Okay, I'll explain everything on the next example. There's an example just on the next page. Yeah, so the area under the curve in a pressure volume diagram is equal to the magnitude of the work done on a gas. So the area is simply just given by P final volume minus initial volume, which is just the same as P delta V. So let's look at this problem here. Find the numeric value of the work done on a gas in A. So here, in other words, they're just trying to tell you to say, find the area of this shaded region there. So initially the curve was just like this. So you can find a question like this. Then you have 1 there, then you have 3 there. You can find a question like this in an exam, and then they ask you to calculate the work done in the whole process. So the work done in the whole process is just simply the area under the curve. So the area under the curve is this one, and then we're going to divide it into 2 parts so that we can find it properly. If you want, you can use the area of a parallelogram. You still find the same answer. Yeah, because we know that area of a not a parallelogram, of a trapezium. This is a trapezium. So area is equal to 1 over, you know that it's A plus B times height. So this is how you find the area of the trapezium. And then, this is how you find the area of a trapezium. But in case what you've been given is not a trapezium, you just have to divide it in 2 parts. Not really 2 parts, but in 2 parts, meaning they can be 3, 4 parts, depending with the shapes that you have. Sometimes you can find this has gone this side again, from there it goes down, from there it goes this side, then from there it goes down again. So you have to find the area under the whole curve to find the work done by the whole, the work done during the whole process. So for this question, we will just divide, we just divide this into this part, which is part A, and then another part. So we have A1 and A2 there. So to find the area for A1, A1 is a rectangle. This is a rectangle. So a rectangle is simply just given by length times the breadth. So the area of a rectangle is length times the breadth. So the breadth here is equal to 1. So let's start with the length. The length is just, you subtract this 3 minus 1, which will give us 2. And volume is in meters cubed. So we'll get that 2 and then multiply it with the height. So the height is simply just 1 minus 0, which is just 1. But of course, this one, you're multiplying it with 10 to the power 5. And then the area 1 simply just give us 2 times 10 to the power 5. This will be meter cubed. Yeah, so from there, this is not meter cubed, this is pascals, and then times meter cubed. Sorry, this is meter, it's volume. We're saying, okay, let's just use dimension analysis to get the correct the correct formulas. I mean the correct units. So we have this 2 is the length. So this 2 is the length, which is in meter cubed, the volume. So we have meter cubed from the length. And then let us also find this one. This one is a Pascal. So let us just keep that. Let's say meter cubed Pascals. Okay. So we just write it like that. But we know that a Pascal is equal to a Pascal is just the same as Newton over what? Oh, sorry, Newton per. Let me just use per. It's Newton per meter squared. That is a Pascal. Yeah, that is a Pascal. Newton per meter squared. And then Newtons is simply just a Newton is simply just kg kg meters per second squared. Anyway, let us not go this far. Let us just keep this. This is okay. Yeah, but if you want, we can just replace a Pascal there so that we get rid of the m squared. But anyway, even this is okay. Yeah, even this is okay. But we know that okay, this can also be written as a joule. So this one is a joule, in other words. Okay, so area 1 is equal to that. And then let us also find area 2. So area 2 is a triangle, and this is a right angle triangle. So we can find the area of that as half base times height. So this can be written as half. The base there is 3 minus 2, which is just 2 times the height is also 3 minus, 3 minus 1, which gave us 2. And then the height is also 3 minus 1 there, which will also give us 2. But of course, this 2 is a pressure, so it should have 10 to the power 5. So this will just give us 2 times 10 to the power 5 as the answer, because these 2 cancel with that 2. So area 2 will just be 2 times 10 to the power 5 as well, but in joules. Okay. So let us now okay. Let us now find the total area, which is the work. So work could just simply be A1 plus A2. So when you add this plus that, the answer that you get is simply your work. So when you add this and that, you get this is 4 times 10 to the power 5 joules. So this one is the work done on the gas. It's the work done on the gas, and it's positive when the arrow is moving from a higher volume there going to the lower volume. But this time around we have it's moving from the small number going to the bigger number, meaning the final is bigger than the initial there. So we expect our work to be negative. In normal cases, we know that if the work done is on the gas, the area, that's when the area is going to be negative. But for this, we know that the area, after calculating the area of this, the answer that you always get is the work done on the gas. Yeah, the answer that you get is the work done on the gas. But if what can I say? The answer that you get is the work done on the gas. But if you look at the actual, the actual formula, we said the work done on the gas has a negative in front there, negative P delta V. Yeah, a negative P delta V, that's the work done on the gas. And the reason why we get this negative is because of what happens when on the change in volume here. The final answer is smaller than the initial answer. But in this case, when you check, the final volume is bigger than the initial volume. So meaning when you subtract the two, you get a positive answer. But we know that the answer that we're supposed to get should be the work done by the gas. I don't know if you're getting the explanation, the work done by the gas. And then in this case, we have, okay, we know that this PV diagram is showing the work done by the gas. It's showing us the work done by the gas, and the answer that we've gotten is positive because it's the work done by the gas. But if it's the work done by the gas, and then after calculating this, we always find the work done on the gas, it means that we have found the opposite of the answer that we are supposed to find, meaning we are supposed to add a negative in front of them. But if the arrow was pointing down, or if the arrow was coming this side, we would have left it positive like that. Okay. So that's the answer there. All right, so let's look at the first law of thermodynamics. So before we look at the first law of thermodynamics, we are going to first define thermodynamics in a slightly different way from the way we defined it, but it still means the same. So thermodynamics is simply just a name given to the study of processes in which the energy is transferred as heat or work. So we're going to be defining thermodynamics in this chapter as a process in which energy is transferred in the form of heat and work. Previously, we defined it as a link between the different energies. I mean, between heat and other types of energies. Yeah, like kinetic energy, other type, chemical energy, other types of energies. Yeah. But in this case, in this chapter, we defined it, we're going to define it, or we're going to take it as the process in which energy is transferred as heat or work, heat and work, sorry. So let us look at this. Okay, internal energy will still be defined the same way we defined it at the beginning, which is just the sum total of all the energy of molecules within the system. All right. So the internal energy of a system should increase if the work done on the system, or if the work done is on the system, or if the heat is added to it. So the internal energy are going to be representing the internal energy with delta U, that is the change in the internal energy. So we expect this change in the internal energy to increase if the work is being done on the system. So we know that if the work is being done on the system, the work will have a negative sign. And then if the work is done by the system, work will have a positive sign. And then the other time when we expect the internal energy to increase is when you heat something, or when heat is being added to the system. Imagine you have something like this. It contains molecules there, let's say molecules of water, and then you decide to heat this. Before you heated it, let's say maybe before you heated it, the energy was, I'll just represent it by E. The energy there maybe was 2000. Okay, the energy there was maybe 2000, yeah. And then when you heat this, you expect some energies like kinetic energy to increase. Potential energy reduces the kinetic energy of the molecules there. You also have other types of energies increasing there. Thermal, you have a lot of other energies increasing in this container. So that's why we're saying if the work is being done on the system, the energy there will increase. Same applies to a piston. If you have a piston and then it's like this, huh? And then you decide to start pushing this piston down. You decide to start pushing the piston down. It means that here you expect the thermal energy to increase. Why? Because you are compressing the molecules. And then when you're compressing the molecules, they'll have nowhere to go to, but they'll start heating up. I don't know if you know the concept that works in a pump, the bicycle pump, the one that you use to pump air into the tire. Yeah, that's why after pumping the air into the tire, the pump itself becomes hot. It's due to the same concept. So when you press the piston down, you expect this pump, or rather the cylinder, to get hot. So the cylinder will be hot because you are trying to increase the you are doing work on the system. Yeah, it's because you are doing work on the system. That's why the energy is that's why the internal energy of the system is increasing. Yeah, so this internal energy is simply just given by work plus the heat energy there. Yeah, so work plus the energy there gives you the internal energy. Okay. So what else can I talk about on this? I think that's all. Yeah, so the internal energy increases when you add heat to the system, or when work is being done on the system. Okay. So remaining with 10 minutes, I'll send another link in case it ends before we finish. All right, so similarly, the internal energy should decrease if heat flows out of the system, or if work is done by the system on something in the surrounding. Yeah. So the first law of thermodynamics is another conservation law, which relates the change in internal energy and the energy associated with the position and motion of all the particles of a system, and the energy transferred and the energy transfers due to the heat and work. Yeah, so they are just trying to talk about the formula here. The internal energy is equal to work plus the heat. Or in most cases, you find it as heat plus work. Yeah, but in most books, you find it like this: internal energy is equal to Q minus W. Still the same. You just have to know which one represents when work, which one you use when work is being done on the system, and when the system is the one that is doing work. All right. Any energy Q exchanged between the system and the environment, and any work done through the expansion or compression of the system results into a change in the internal energy of the system. So this is what I was just talking about. Yeah, so they are saying a change in the internal energy results in measurable changes in the macroscopic variables of the system, such as the pressure, temperature, and the volume. So if the internal energy of the system changes, you expect the temperature to change, you expect the volume to change, and the pressure to change. So I've talked about all this where I said, if you have that part where I was explaining the water in a container, then when you heat it, and I also talked about the piston when you're trying to compress the air in the cylinder. I mean the air in the cylinder. Yeah. So this is what I was talking about. That's what this point is talking about. You expect the temperature to increase, you expect the pressure to increase, you expect the volume also to change. It can either increase or decrease. Same applies to the temperature, it can either increase or decrease. Same applies to the pressure, which can also either increase or decrease. So what they are talking about, I've explained already. So the relationship between the change in the internal energy, the energy and the work done on the system is given by the first law of thermodynamics. So what I wrote here, change in internal energy is equal to Q plus W. This one is the one that we call the first law of thermodynamics. So this is the first law of thermodynamics. So the work here is being done on the system. So if it's the system that is doing work, you expect the formula to be the change in internal energy is equal to Q minus W. So when you find this, you need to know that it's work done by the system. And then this one is the work done on the system. If you are dealing with gases, you can say this one is work done on a gas. This one, a gas is the one that is doing work. Meaning if you are dealing, in a case of a piston, it means that the piston is moving up because the work is, because the gas is the one that is doing work on the environment, or it's the gas that is, or it's the system that is doing work, in short. Okay, so let's quickly move on. So if a system undergoes a change from the initial, a change from an initial state to the final state, then the change in the internal energy is given by the formula below. So I've explained this. So the change in the internal energy will just be UF minus U initial is equal to Q plus W. That is if the system is the one, that is if the system, if work is being done on the system. Yeah. So where Q is the energy exchanged between the system and the environment, and W is the work done on the system. So the quantity Q is positive when energy is transferred into the system. So when you're adding heat, the quantity Q is positive, and then when you're removing heat from the system, or when the system is losing heat, you expect the quantity Q, meaning the energy, to be negative. So if the system is losing heat, the energy will be negative. If the system is gaining heat, the energy will be positive. Okay, let's look at this figure here. So the figure below illustrates the first law of for a cylinder of gas, and how the system interacts with the environment. So when you add heat to the cylinder, you expect the gas inside the cylinder to expand. As it is expanding, to begin to push the block here, the block will begin to go this side. So let's assume that here there's no friction. So the block will begin to go this side. And as that happens, you expect to have the work that is that the system is doing on the environment to be positive, and then the work that is being done on the system to be negative. Right, so the gas cylinder contains the frictionless piston, and the block is initially at rest. Okay, so energy Q is introduced into the gas as the gas expands against the piston with constant pressure P until the piston hits the stop. Until the piston hits the stop, it exerts a force on the block which accelerates on the frictionless surface. All right, so let's just quickly move on. Let's look at the thermal processes in gases. Thermal processes in gases. So we know all these. That's why I was saying the slide today is very short. So when we talk about isothermal, an isothermal process, we know that the temperature is constant there. And if the temperature is constant, it means that the change in temperature there will be zero, which makes the internal energy also to be zero, meaning Q is equal to be, meaning Q is just going to be equal to W. So if T is constant, you have the internal energy is equal to Q minus W. And then if T is constant, it means that the internal energy will be zero. Yeah, the internal energy there will be zero, meaning you just make Q or W, the subject of the formula, which will just be Q is equal to W. This is what they're trying to illustrate here. And then when you talk about isobaric, it means that the pressure is constant. And then when the pressure is constant, you have Q is equal to the change in internal energy plus the work there, which can also be written as the change in internal energy plus P delta V. All right, so then when you have isovolumetric, which is also known as isochloric, something like that, V there is constant, and when V is constant, the change in volume is constant, meaning the work done will also be equal to 0. So you just have Q being equal to the internal energy because you don't have the volume there. And then when you talk about an adiabatic process, meaning Q is equal to 0, meaning the change, there is no heat that is entering or leaving the system. Yeah, meaning you only have the change in internal energy to be negative W. So you should find time to look at this. What I've just explained on this table is what is happening here. So this is isovolumetric, this is isothermal, this is isobaric. Yeah, so in this case, I think that's the end of the lecture. So I can say, because we've only remained with seconds. I don't know if you have questions. If you have questions, I can make another link so that I give you time to ask questions. If you don't have questions, we end here. I'm going to send the exercise. Okay, thank you very much for your attention.